This is Algebra 2 with trig. This is the review for 7.1 to 7.4. This is page number 3. We're going to find the inverse. So find the inverse, we're going to switch the x and the y. Now this is a logarithm. The inverse of a logarithm is exponential. So we're going to say 8 to the x power equals y. And that's the only thing we need to do to get y by itself. So that is the inverse of our logarithm. Here we have ln. That is a logarithm. That is a logarithm with a base of e. So we switch our x and the y. We take our base to the x power equals, so e to the x power equals y plus 1. We're going to subtract 1 from each side. So now we have y all by itself. Here we're going to switch our x and the y. Now this is exponential form. There's no logarithm involved with this. This is exponential. To find the inverse, we're going to use a logarithm. So we're going to say log. The base is going to be the 7, just like the exponential. You know that a logarithm always equals the exponent of x. Here we're going to switch our x and the y when we're trying to find the inverse. We're going to add the 2. Now we have a exponential form. We have an exponent that we're trying to solve for. So we have to solve it by using a logarithm. Since the base of the exponential is 3, the logarithm is going to have a base of 3. You know a logarithm always equals the exponent. And this whole portion is what you're taking the log of. 3 to what power equals x plus 2? 3 to what power equals x plus 2? To graph these, to make a table, we want to switch this over. We don't want to do the inverse, but we are going to write it as exponential form. We didn't switch the x and the y. We just did the exponential right there with that logarithm values. So we're actually trying to do the log base a half of x. So for us to calculate this, we're going to pick values for y that help calculate the x. So we have 0, 1, and negative 1. When the y value is 0, we get 1. When you plug in a 1, you get your base. And when your exponent is a negative 1, you get the reciprocal of your base. And if you want to push that a little bit further, you could do negative 2, which would flip it and square the 2, which is 4. And you might even be able to do 3. Negative 3 would flip it and cube the 2. So that just gives you an idea of where it's heading. So that's our graph, y equals log base a half of x. We have an asymptote that is horizontal at x equals 0. I'm sorry, you weren't able to see any of that graph. So we plotted our points. We traced it out. We put in our asymptote and wrote our equations. The asymptote was x equals 0. It's going to be vertical for every logarithm. It's always the k value. The domain, it switches from the exponential form. The domain is not y equals. The domain is x equals. But notice that it is greater than the 0. So x is greater than 0. It's greater than the asymptote. The range, that's going to go on forever in both directions, up and down. The end behavior, it doesn't approach the left forever. It only approaches the asymptote, and the asymptote is at 0. When that happens, the graph is going up. The graph does have x values that get bigger, and when that happens, as x values get bigger, the y values, let's see, looking this direction, actually, the x values are getting bigger, the y values are going down. This equation has a translation. So when we do our table, we're just going to be looking at y equals log base 3 of x. So to do that, we're going to do the exponential form, which is 3y to the x. So we're going to pick values for y, 0, 1, and negative 1. 0 gives us 1, 1 gives us our base, negative 1 gives us the reciprocal. So when x is 1, we're at 0. When x is 3, we're up at 1. And when x is 1/3, we're at negative 1. So we're going to write y equals log base 3 of x. Now we're going to take every one of those points and we're going to translate it to the right and 1 up. So 2 to the right, 1 up, 2 to the right, 1 up, 2 to the right, and 1 up. So that gives us this asymptote here at x equals 2. Gives us an equation, log base 3 of x minus 2 plus 1. The x minus 2 means it moves 2 to the right. So the asymptote was x equals 2. The domain was values that were greater than the asymptote. The range went forever up and down. The end behavior, we approached 2, and when we did that, the graph went down. And as x got bigger, the y values got bigger. Now here we're going to tell if each function is exponential growth or decay or neither. Now this is going to be exponential growth, because A is greater than 0 and the B value is greater than 1. Here, the A is greater than 0 and the B value is less than 1, but greater than 0. So this is exponential decay. Now this base, the B value is greater than 1 because it's E. E is 2.718. The A value is greater than 0 because it's 63. Now, an exponential would look like that. But this has a negative value there, so it's actually going to reflect over the y-axis. The R value is less than 0. So it's exponential decay. Here we see that the A value is less than 0. The R value is less than 1. We're not as worried about that. We just want to be sure that we are greater than 0. So what we have here, our base is still 2.718, which would typically come down in that fashion, but now we are going to have a graph that does that. That is neither exponential growth or decay. It's neither in terms of growth or decay, but it is still considered exponential. Here we have an A value less than 0, so that's enough to say neither. But it is exponential. In this case, the A value is greater than 0, and the R value is greater than 0. So that's exponential growth.